not go there first, and the electron will go to a lower energy subshell before it goes to the higher energy subshell. So that's why the electron does not go to 3D first, and it goes to 4s first, and then fill up with 3D. After 3D, you get your 4p, 5s, okay? And then after 5s, you may think, well, we're going to go to 5p. No, for 5p, actually, we're gonna actually come back here and go to 4p off. So as you can see, it's not 1s, 2s, 2p. Well, 1s, 2s, 2p, that's in correct sequence. But after the 2p there, 3s, 3p, the correct sequence after that would be 4s, not 3d. And so you see some of the things that start jumping out of the line. That's because the energy levels start to cross over with one another, especially with the subshell. Okay, so, and that's where the exceptions come in, especially with the transition metal elements there. And you will, when you read chapter 8, you will see all those different exceptions in there. And for each individual exception, there is a theory and there's an experimental observation, and then along with the theory to explain why the exceptions is the correct case there. So when we're talking about electron filling, we do not need you to memorize the electron distribution for each and every single element there. We just need you to know the basic rules. But when you look at a particular elements, and if you see an exception that doesn't follow the general rule, those are the exceptions there. And your textbook, for each exception that your textbook talks about, and you will see an explanation why we have those exceptions there. We will mention some of those exceptions in class as well. So this is how we fill the electrons, and this is the rules of governing the electron filling. Okay, now let's take a look at a particular element, atoms of a particular element, sodium. And if you look at sodium, sodium number 11, Z, the atomic number 11. That means you have 11 protons, you have 11 electrons. How do we distribute those 11 electrons? Well, according to the sodium there, according to the rules that we talked about, we have 1s, 2s, so you have a total of 11 electrons there. Electrons will go to the lowest energy orbital available. So 1s, we can put 1 in there. We can put another 1 in here, so 2 electrons. You got 11, 9 left. Okay. When the third electron comes in, you have to go to the higher level. 4 electrons are being used out of the 11. You have 7 more left. Okay. And according to the rules that we talked about, 3 orbitals in here. Each one will be occupied by 1 electron first. Well, that's 3 plus 4, that's a total of 7. We still have 4 more electrons to need to be distributed. So these rooms are half occupied. We're going to pair them up. That takes care of 10 electrons. We have 1 more electron. And that electron will have to go to the 3s orbital. So the way that I draw on the board here is that it takes forever on PowerPoint and trying to rearrange those different energy levels here. So they're all on the same level, but on the board it's much easier. And what we want to indicate here is that each level has a slightly different energy. It goes up for each of the suborbitals that we have there. There's a difference in energy there. So this is what we have, the electron distribution. For sodium, this is how the 11 electrons being distributed. Another way to represent the electron distribution is that for the 1s orbital, you get 2 electrons. 2s orbital, 2 electrons. 2p orbital, total of 6 electrons. 3s orbital, 1 electron. Okay, so this is what we call the spectroscopic notation. 1, 2, 3. That's the n number. The superscript 2, 2, 6, 1. That's the number of electrons on each sublevel. Okay. Now, when you look at the electron distribution, when you look at the spectroscopic notation, for elements like hydrogen or helium or sodium, we don't have a whole lot of electrons in there. But for elements that has, say, 100 electrons there, if we ask you to write out the electron configuration in this way, it could be a mile long. Well, chemists are lazy people. If they have a shorthand and they don't want to do complicated ways there, so we introduce what we call the core or noble gas notation. Okay. If you look at the electron configuration for helium, helium only has 2 electrons. Okay, so the electron configuration for helium will be 1s2, 2 electrons in it. If you look at neon, neon has a total of 10 electrons. Okay, this is how the 10 electrons are being distributed. And if you look at argon, argon has 18 electrons. This is how the 18 electrons are being distributed. Using this, we can create an abbreviation. We can use an abbreviation to represent different types of elements there. And let's take a look at magnesium. Magnesium, if you look at the periodic table, number 12. Number 12 means you have 12 electrons. So the full electron configuration would be 10 plus the other 2. So 1s2, 2s2, 2p6, 3s2. However, if you compare this with this part is identical. So why bother to write everything out for the neon electron configuration? Let's use a core notation or noble gas notation. Let's just put neon in a bracket and then put 3s2 in there. Now this represents this part, which is identical to the first part. Okay, so this is what we call the valence electron. This would be the core electron. Okay. So representing electron distribution is our ultimate goal. Understanding electron distribution is our ultimate goal. Once we understand how the electrons are being distributed, we will be able to predict how a particular atoms of a particular element will behave. So we need to develop different ways to represent the electron distribution. And full electron configuration is one of the methods, and then core notation or noble gas notation is another. And we just need you to understand when you put the symbol of the noble gas element in the bracket, that represents whatever electron configuration that we have for that particular noble gas element. And in addition to that, we have extra electrons. We put those extra electrons. We put those extra electrons after the noble gas electron configuration. Okay. So in this case, the outermost electrons are referred to as valence electrons. Only the valence electrons participate in chemical reaction. Core electrons do not. You ask the question, why? Well, everything has something to do with the energy. When we look at the periodic table later on in this chapter, we will look at the amount of energy that is required. We can actually simulate, we can actually do the experiment in the laboratory to verify the amount of energy required when you try to touch the core electron. And comparing that to the valence electron is the core electron energy required to touch the core electron is much, much higher than the energy required to remove or add the valence electrons. Therefore, the core electrons do not participate in chemical reaction. Only the valence electron participate in chemical reaction. And therefore, the valence electron determines the chemical property. And knowing the valence electron, number of